The next topic concerns kinematics of rigid bodies. As you'll recall, kinematics is the topic of describing motion, so the tools we have to relate position, velocity, and acceleration for the motion. And previously we had worked on particles, where particles are objects whose orientation doesn't matter to us. Now we're going to begin working with rigid bodies. These are objects whose orientation does matter to us, so they have some dimension, shape, and so forth that are important to incorporate into the kinematics and the kinetics that we'll do later. You can separate kinematics of rigid bodies into 5 categories generally. The most basic is translation. So this object is an arbitrary rigid body, as is this one. So in translation, points on the rigid body follow parallel paths. These paths may be curved for curvilinear translation, or they may be straight for rectilinear translation. The second category is rotation about a fixed axis. So imagine that this axis is the axis of rotation. It's fixed, it doesn't move, it doesn't change its orientation or anything, and the object revolves around that. So any point on the rigid body is going to subscribe a circle around that axis of rotation. The third category is general plane motion, which we express as a combination of translation and rotation. Imagine this bar with 2 sliders moving in this plane, but the rigid body stays in a single plane, but the motion is a combination of translation and rotation. These are the 3 topics that we're going to consider. More advanced dynamics courses involve motion about a fixed point, for example a top spinning on a table where it spins but the bottom contact point stays in one point, so it has 2 axes of rotation. And then the most complex is general 3-dimensional motion. Let's begin by talking about translation of rigid bodies. So suppose we have a rigid body, that's this arbitrary shape, and it's undergoing translation. And we have 2 points that we will label on the rigid body. Here's point A and here's point B. Okay? We can describe the relative position of these 2 points from our relative position equation we saw before, where the position of B relative to A is equal to the position of B minus the position of A. Or written another way, the position of B equals the position of A plus the relative position. Okay. So if I tell you what the position of this rigid body, if I tell you the position of A and the relative position between the 2, you can tell me what the position of B is. And that's the foundation from which we develop most of our concepts of kinematics for rigid bodies. Okay. Now, a rigid body, being rigid, that is, it doesn't bend or stretch or anything like that, it maintains its shape. That means that the position vector B relative to A is not going to change length, okay, or size. Also, because we're in translation, that means the orientation of the rigid body is constant. It doesn't rotate, okay, change its orientation. It maintains that orientation, as shown in this picture, as the points either subscribe curves or straight lines or what have you. So, with that in mind, we can take the derivative of this relative position equation with respect to time. And if I do that, I get R sub B dot, the time rate of change of the position vector of B, equals R sub A dot, and the time rate of change of the relative position vector is 0 because it doesn't change its length because its body is rigid, and it doesn't change its orientation because we're in pure translation, no rotation. And so that's what we conclude. Or written another way, we can say that the velocity of B equals the velocity of A. So for a rigid body undergoing translation, all points on the rigid body have the same velocity, same magnitude, and in same direction. Okay? And similarly, the acceleration is always the same for any points on a rigid body. So if I tell you the motion of one point on the rigid body, say it's position A, I tell you its position, velocity, acceleration, you can tell me the position, velocity, and acceleration of any other point on the body if you know the geometry, that is the position of points relative to each other. So when it comes to translation of rigid bodies, really this is all there is to it. All points have the same velocity and acceleration. Now let's consider the next category of motion, and that is rotation about a fixed axis. So here I have a picture of an arbitrary rigid body, okay? And let's suppose it's rotating about a fixed axis, and that axis corresponds to the z-axis. Okay, so my rigid body is spinning about this z-axis. The z-axis doesn't change orientation or anything, right? So if you look at any point on that rigid body, say point P here, it's going to subscribe a circle centered on that axis. Okay. When we talk about rotation about a fixed axis, one thing that's important is you determine the positive rotation direction by the right-hand rule. So more on that in a moment. Okay, so we have this body rotating about a fixed axis. Here's the origin. The position of an arbitrary point P is there. Here's the position vector for that arbitrary point. Okay, and I think you can imagine, if you can visualize this three-dimensional shape, that if P is following this circle, rotating about it, then tangent to that circular path is going to be the velocity of P. And we want to come up with a relationship to describe that velocity. Okay, and if the angular change relative to the x-axis is theta, okay, and we're looking at how theta changes with respect to time. And a note on units: 1 revolution is equal to 2 pi radians is equal to 360 degrees, just units of rotation. Okay. Okay, now the velocity of P, this velocity vector, is going to be, first of all, perpendicular to r and perpendicular to the plane created by the position vector r and the axis of rotation z. Okay, so it's going to be perpendicular to that. So what we want to do now is we want to define the angular velocity. The angular velocity is a vector, and we will use lowercase omega. That's not a W, that's omega, the lowercase Greek letter. And for angular velocity, an angular velocity is a vector. So the angular velocity is equal to, right, the time rate of change of this angle, theta. So theta dot, it's how fast it's spinning around that axis. And that's and now that's the magnitude for the direction. Okay, in this case we chose z to be our axis of rotation. So the direction of this vector for omega is going to point in the same direction as z, which is the unit vector k. Now in this case we chose the our coordinate system x, y, z such that z corresponds to the axis of rotation. And that means that the direction of our angular velocity is going to be in the same direction. But it's important to note that this can point in other directions besides the k or z direction. Okay? We'll see more examples of that later. For now, we're going to assume that our angular velocity vector points in the z direction. And the positive direction for the angle and omega is defined according to the right-hand rule. So in this case, if the z-axis is positive this way, the positive direction of rotation goes by our fingers. So the positive theta direction is just like this arrow, right, that way. So if you know the direction of rotation, you can find the positive direction of your angular velocity, or if you know the angular velocity direction, you can find the direction of rotation by the right-hand rule. Now, another way to write this is the magnitude of omega is just equal to omega, which is theta dot. Okay? Now, given this definition for angular velocity here, we can come up with an equation for the velocity of the point P. And the velocity of P, the vector, is equal to omega, the angular velocity vector, cross with the position vector r. And that is the equation for the velocity of a point on a rigid body rotating about a fixed axis. Okay? An important thing about this equation is that the origin from which you measure the position vector, r sub p, that origin can be anywhere on the axis of rotation. So here we've shown it right here. We could just as easily write this equation for an origin that was here. Okay? And use that position vector, call it r prime. Okay? And we would get the same velocity. But it must be on the axis of rotation. That is the origin from which you measure the position. Okay? So the velocity is pretty straightforward. For rotation about a fixed axis, omega cross r. You have to do a cross product. A lot of times that's not that difficult though. Now if we take that relationship for velocity and differentiate with respect to time, we'll get the acceleration. So the acceleration is equal to the time rate of change of velocity. Right, so that's the time rate of change of omega cross r. Right? And now we can use a chain rule-like property to do this, to expand this derivative. So it's going to be d omega dt cross r. Remember, we have to preserve the order, plus omega cross with dr dt. So that's an expression for the acceleration of the same point. I guess I could have subscripted that point P. Okay. We can simplify this or make this more useful if we note a couple of things. First of all, dr dt is just equal to the velocity. We see that here, okay, which is equal to omega cross r, right? Next, we want to define the angular acceleration vector. And for angular acceleration, we use the lowercase Greek letter alpha, and again it's a vector just like angular velocity, and that's equal to d omega dt, the time rate of change of angular velocity. We can write that as omega dot k in this case because our axis of rotation corresponds to the z-axis, so the direction is k, and another way to write that is theta double dot times k. Or we could write this as alpha times k. Just lots of different ways of writing it. Okay, so making use of this definition for the angular acceleration vector and noting this definition, we can write the acceleration for a point on a rigid body is going to be alpha cross r plus omega cross r. So that is an expression for the acceleration of any point on a rigid body undergoing rotation about a fixed axis. And that is paired with the velocity equation we saw a moment ago, which is the velocity is omega cross r. Something interesting about this acceleration vector that we defined a moment ago. The acceleration has two components. We've got one that's alpha cross r. And you can show that the result of this cross product points in the same direction as velocity. And we've seen something like that in the past for particles undergoing motion, curvilinear motion, and that corresponds to the tangential direction. So the tangential acceleration is alpha cross r, okay? And we can write it that way, a sub t equals. And then that means the other component is the normal acceleration, which is omega cross r. And this vector you can show the result of omega cross r points towards the axis of rotation, just like the normal acceleration of a particle. Okay, so rotation about a fixed axis. These two equations are the important ones to remember. Just as an example of rotation about a fixed axis in a machine, here's a picture of a gear train. We have a horizontal axis here rotating this way, the vertical axis here turning that way, attached to another gear. And you would, in designing this transmission system, you would be interested, for example, knowing that this axis of rotation, right, for that middle gear train would be pointed this way. You might be interested in finding velocity and acceleration here, or velocity and acceleration here at these contact points, in order to determine stresses and loads and things like that. You would need to do a kinematic analysis of this system, which is rotating about a fixed axis, this shaft, in order to find the velocities, accelerations, and so forth to do a full design. Just a little example for acceleration about a fixed axis. I'm sorry, rotation about a fixed axis. If we take the rigid body that's rotating about a fixed axis and take a slice, planar slice through that rigid body that's perpendicular to the axis of rotation, we'll be looking at something like this. So here's x and y, z, the axis of rotation is coming straight out of the page, like this. And so according to the right-hand rule, if this is the direction of the axis of rotation, then the positive direction for rotation is this way, counterclockwise. And so we see here our vector omega is equal to omega k, as we noted before. This point is fixed, it doesn't move on the rigid body, and it all rotates about this point in that direction. So here's the point P that we're interested in, here's the position vector of that, and here's the velocity, which is perpendicular, because this point is moving in a circular path like that, just like the motion, circular motion that we saw for particles. Okay. So since omega equals omega k, like we have here, right, positive motion omega results in counterclockwise rotation. Now, as we saw before, the velocity of that point P is going to equal omega cross r, right? Which is equal to omega k cross with the position vector. So we can't find the magnitude of this cross product because we don't know the length of r or omega, but we can find the direct hand rule again. You point your fingers in the direction of the first vector, which is the z-axis out of the page, curl them towards the second, this way, and your thumb points in the direction of the result, right? Which means the resultant vector is perpendicular to r in this direction, okay? By the right-hand rule, and since they're perpendicular, since z and r are perpendicular, so as we mentioned before, it's perpendicular to the plane defined by the z-axis and r, and in magnitude it's equal to r times omega. So that's an important relationship. Imagine trying to find the velocity of a wheel that's spinning about the axle. You've probably seen this relationship, r being the radius, the distance out to the edge of the axle or to the edge of the wheel. Omega is the angular velocity. Okay. Similarly, we note that omega k cross with omega k cross with r. We can also infer the direction at this point, which is the same direction or the opposite direction of r. So it points in the minus r direction. So that is this direction. So that is the direction of the normal acceleration, right? So from that we can say then that the acceleration of the particle is equal to alpha k cross r. We haven't learned anything about that, but the second term, which is here, minus omega squared times r. Okay, and the tangential acceleration, right, is equal to r times alpha, and the normal acceleration is equal to r omega squared. We can come up with equations for the motion in rotation about a fixed axis. Imagine we have a wheel that's rotating by omega, has a radius of r. Perhaps it has an angular acceleration as well of alpha. Just like with rectilinear motion in particles, for rotation about a fixed axis, suppose we want to know this point P, what's going on there. If you know theta for all time, then we say that the motion is known because we can integrate to find the velocity and acceleration. For example, omega equals d theta dt, and alpha equals d omega dt. It also equals the second derivative of theta with respect to time squared. Or we can say that alpha is equal to omega d theta. So each of those equations we can separate and integrate, and given appropriate constants of integration, solve for the motion, just like we did in kinematics of particles. For example, in the situation of uniform rotation, that is when alpha is equal to 0, we know that the angle is equal to the initial angle plus omega times time. So we can find the position at any time given the angular velocity. If we know that the angular acceleration is equal to a constant, then we can say that the angular velocity is equal to the initial plus alpha t. And the position, the angular position, is equal to initial plus omega t, sorry, not omega naught, omega naught t plus 1/2 alpha t squared. You'll notice the parallel between these equations and those for motion of particles. Also omega squared So all of these equations, if we know that angular acceleration is a constant, we can find the angular position, angular velocity for all time, given rotation about a fixed axis. Now we'll begin on the third category of rigid body motion, which is general plane motion. And we can use these concepts anytime a rigid body is moving in a two-dimensional plane. The interesting thing about plane motion is we can conceptualize this motion by splitting it up into components which are, first of all, translation and then rotation. So we can separate those two conceptually, building on what we learned previously, in order to build up the kinematic equations. Okay? So suppose we have a rigid body, this guy, and 2 points on it, A and B, and initially they're in an orientation like this, and then the full motion takes A1 to A2 and B1 to B2. But we can conceptualize it as first a translation of the rigid body from A1 to A2, B1 to B1 prime, and then rotation about a fixed axis centered on A2, like that. And we can use those concepts to build up the notion of general plane motion. So, building on this notion of relative motion or using combinations of translation and rotation for the velocity of a rigid body. So, suppose we have this bar that's connected to sliders at either end, and we are given information about the geometry and the velocity of part of point A at this end. And we want to find the velocity of B at the other end. Well, we can write this equation as follows. Here's the velocity of B, and that's equal to, first of all, the translation component. Remember, when a rigid body is in translation, the velocities of all points are equal. So that means the velocity at this end is going to equal the velocity of this end. So the velocity of B for the translation part is just equal to the velocity of A. So we'll write that here, velocity of A. Then we have the rotation component, and we imagine that this rigid body is rotating out about an axis centered on A, right-hand rule, so rotating this way. Here's A. Imagine now for this component it's fixed, and it's rotating about that fixed axis. Well, that's the velocity of B relative to A. All right? Imagine, for example, you're sitting on point A, you're a reference frame that doesn't change orientation, follows A but doesn't rotate, and you're watching B. It will look like B is moving in a circle about you. Well, we came up with a relationship for that kind of motion. It's rotation about a fixed axis. So we can say then that the velocity of B is equal to the translation component, velocity of A, plus the rotation component, which is omega cross R. But this position vector R is the position of B relative to A. And so that's the kinematic relationship for general plane motion velocity relationship. Well, usually if we have motion in a plane, we can choose that plane, select the coordinate system such that that plane is the XY plane, so the axis of rotation is the Z-axis, right? And so we could write this furthermore as, more specifically as the velocity of B equals the velocity of A plus omega K cross R. And that's the position of B relative to A. So on this picture, that vector is this one. So that's another way of writing it. We can use this one if we know that the axis of rotation corresponds to the z-axis or the k direction. Something important to note here that's this angular velocity vector. The angular velocity vector for a rigid body is the same anywhere on that rigid body, or a better way to put it is that it doesn't have a fixed point of reference. So in this example we're finding the velocity of B. What if we decided to then go ahead and find, the velocity of point C? We would be using exactly the same angular velocity vector because it doesn't change. Or if we want to do B to A or C to A or some other combination, the angular velocity vector of this rigid body is the same no matter what position we're talking about, whether it's A or B or some other point C. So that's important to keep that in mind as you work these types of problems. So that's how you find velocities for general plane motion. It's as simple as this equation. This is the most general one. Okay? The velocity of point B just equals the velocity of some other point on the rigid body plus omega cross R. And important that R is B relative to A. Okay? There's another tool that's useful for finding velocities on rigid bodies, and it's the concept of instantaneous centers. Okay? When you're undergoing general plane motion, like this rigid body, it has some velocity, has some rotation, right? You can relate the velocity, right, to rotation about an imaginary point C, which is the instantaneous center. Okay? You can find that point if you know the velocity of point A. This is the velocity vector here. you know that the center about which it's rotating, if it were rotating about a fixed axis, is going to be perpendicular to that axis, like this. It's going to be somewhere along that line, and the distance that it's going to be is equal to the velocity of the point over the angular velocity. Right? That's just the relationship for rotation about a fixed axis, right? So here's this point C. So at this instant, or at any instant, at this instant, it appears as if this rigid body is rotating about fixed point C. Okay? Now the interesting thing about C is that this instantaneous center is it will move with time. So this concept of this being the instantaneous center is only valid for an instant. A moment later, C may be some other position. Okay? Another thing is that this point C is not necessarily on the body. Okay? So for this concept of finding the instantaneous center, again, this is for general plane motion, that the object can be rotating and translating, but there is a point somewhere in space that will appear to be, the object will appear to be rotating about at that instant. And if you find that space, then you know that the velocity is just going to be equal r times omega in that case. Okay? So how do you find these instantaneous centers? Well, we find them geometrically. Okay, so for example, if we know the velocity of 2 points on a rigid body undergoing plane motion, for example here we know that this is the velocity of A and here's the velocity of B. We know that the instantaneous center is going to be along a line perpendicular to both of those velocity vectors, right? So here's a line that's perpendicular to the velocity of A, here's a line that's perpendicular to the velocity of C. And so where those two lines intersect must be the instantaneous center, right? So that's a geometric approach to finding this instantaneous center. If the two velocity vectors happen to be parallel, like in this case, here's the velocity of A, velocity of B, right? Then we know that it's going to lie along a perpendicular line, right? But we don't know where along that line. We find that position by connecting the tips of the two vectors with a line like this. And where those two intersect is our instantaneous center. In this situation, you can use similar triangles and the lengths of the two velocity vectors to find the location of C. As I mentioned, important thing to remind you of, first of all, C is only valid for an instant. A moment later, as this moves, it will be in a different location. This point C is not necessarily on the body. It's not necessarily off the body either. That C could be located on the body. Another thing, you cannot use instantaneous centers to find accelerations. Right, so that's an important one to consider. If you find C is located infinitely far from the body, in other words, these two perpendicular lines never intersect, okay? That means omega equals 0. You have a situation of pure translation. Okay. And one more thing about this, whenever in any situation where you can use instantaneous centers, you can also always use the general equation for velocity, and vice versa. You can use both of these always work. Sometimes it's easy to find the instantaneous center, usually when you know the velocities of two ends on two ends or two positions on a rigid body. But even in that case, you can always use this approach. I tend to prefer using this approach, the vector approach, all the time instead of instantaneous centers. I'm not sure why I prefer using that, but it just makes more sense to me. But you can also use this approach, and you'll see in the textbook frequently they use this approach. Alright, so that's velocities. That's the velocity equation, or you can use instantaneous centers for general plane motion of a rigid body. What about acceleration? Well, again, we can separate the acceleration of a rigid body conceptually into translation and rotation, and a combination of two. For example, if we know the geometry, if we know what's going on at point A in terms of acceleration and velocity and so forth, and we want to find the acceleration of B, then our relative equation says the acceleration of B equals the acceleration of A, that's the translation part, okay, plus the acceleration of B relative to A. If you happen to be sitting on point A, a reference frame sitting on A that doesn't change orientation but moves along with it, okay, and you watch what B is doing, it will appear to you as if B is moving in a circle around you, right? And so it will appear that B is moving like rotating about a fixed axis. And so we can use our rotation about a fixed axis concepts to come up with the relative acceleration, right? So the acceleration of B is equal to, the translation part is just the acceleration of A, right, plus the angular acceleration cross with the position of B relative to A, plus omega cross R. And again, R is B relative to A. So these two are the terms for the rotation about a fixed axis, acceleration of a point, and this is the translation point. So this equation is the kinematic relationship for acceleration of a rigid body in plane motion. Okay, and that is paired with the velocity equation. So those two equations are the main tools you have for kinematic relationships of motion for rigid bodies in plane motion. Sometimes, frequently, we will assume that the axis of rotation is the z-axis, in which case we can simplify alpha vector to alpha times k. The omega vector becomes omega times k, in which case the acceleration also notice that the term omega cross r there is the normal acceleration, right? You can see that vector here. And also we have the tangential acceleration there, which is this component.